Now I will really fast track through the next slides, and we may take a little bit of this afternoon, perhaps on the rearrangement algorithm, we'll see if that's all right. But I think we have to do something on that. But I will just, of course, I cannot do in 35 minutes a course on risk measures for linear portfolios, risk aggregation, risk allocation. You can write 3 books on that. But let me give you also, in the light of some of these examples, a couple of ideas. And if you find them interesting, you can continue. First of all, we talk about linear portfolios. I already said many times, we work on finance, insurance applications, so we take linear portfolios. Most, of course, in practice, the portfolios are non-linear, and then we linearize. We've seen that in the previous discussions on market risk, linearization. So for the moment, you said, we do it for linear portfolios. We look at portfolios, we have risk factors, we have weights on these risk factors, there are some mean vector, a mean there, and a constant here. That's what we're interested in, d dimensions. Many standard approaches have this, and it's common to use linear approximations. Okay, absolutely standard, nothing special. So we restrict to that. Now this is a theorem I could spend a couple of hours on. But I hope with the little introduction I gave you, you feel, but this theorem is now the generalization of just the last calculation I did on the blackboard and going beyond. Namely, first of all, if you look at my calculation here, and by the way, when we wrote these results, not in the full final form, but close to final form, my colleague in those days, it was a bit of a joke, but my colleague, well, not just in those days, he's still my colleague, Freddy Delbaum. Of course, he's a famous financial mathematician, but he had a very fundamental result, a fundamental theorem of asset pricing. It's about semi-martingale theory and no arbitrage. And of course, I wanted to have also my fundamental theorem. And I said, well, this is the fundamental theorem of quantitative risk management. And I think it is. It will be too difficult to go through every detail, but I hope after this little calculation you will see. First of all, I will go from the bivariate Gaussian. I go to what I would call the nice world of quantitative risk management, elliptical distributions. If the world out there of finance insurance would be elliptical, you wouldn't be here, we wouldn't be here, and we would not have written the book. It's because of the non-ellipticality in stress periods that we have to think about it. But if the world would be elliptical, then everything is beautiful. And this result is perhaps the most beautiful result, and still, I don't think many people capture until now the beauty of this total result. And I think Alex did a lot of work, in really shaping it in the form it's on the blackboard now. It really is in full detail the best you can get at the moment. Let's now go to the theorem. Suppose my underlying random vector is elliptical. Again, you can say, oh my God, what does that mean again? Oh, d-dimensional elliptical, there's a mean vector, there's a variance covariance input matrix. It's not the one of x. But there's this generator function. Oh yes, what was it now again? This generated function, this is not the generator function of the Archimedean copula. Anybody still remembers that psi? It's perhaps there. It's not. You see, that's a problem. That's not your problem, that's our problem. The psi was the generator, the function you find in the characteristic function of the spherical distribution. Now that goes back a long time.
To say it again, it's slide 153.
Yeah, 153. You see, but this is what you have to, once you read these theorems, you must go beyond, in the first reading, beyond this notation. The only thing I'm saying, I go from the Gaussian model, which is elliptical, to the most general elliptical models. I take a spherical, it's like you take a round balloon, that's a spherical. The round balloon is determined by the psi, is the radial part, and then you take the balloon in your arm and you squeeze it a bit. That's the A, and you get an ellipse. You need some nice uniform squeezing. All right? But that's behind that definition. So that, if I just write that, I'm just saying to you, you're in the most beautiful world of quantitative risk management. Okay. Now, the next thing is, again, look at the details. Let rho, it's a risk measure, but not just any risk measure, a very general risk measure. It's positive homogeneous, which we all agreed we must have that to some degree, because somehow for large lambda, so rho of lambda L is lambda rho L for lambda positive. We had a liquidity discussion there. But let's take it homogeneous. That's only one condition. Let's suppose it's translation invariance, and it was René who said, what else can you take? Okay, René, you said that. I remember. So rho of L plus a constant is rho of L plus a constant. That's called moneyness. You measure your risk measure in terms of money. Absolutely undisputable to a high degree. And law invariant, I think this may be the first time I mentioned this word. That means that the risk measure only depends on the distribution function of the risk, not on the individual omegas, if you like. I can think of risk measures where I look at individual realizations. That's a rather general class of risk measures. Why do I introduce that at this level? And this is already in our paper in those days. Is because now the discussion is really going around, should we use value at risk? Should we use expected shortfall? Should we use expectiles? We haven't really discussed them at any length. Should you optimize your portfolio? There are hundreds of papers on optimizing a bond portfolio given value at risk constraints, given standard deviation constraints, given expected shortfall constraints. What are the differences? A huge amount of work. And I'm sure in some of your companies, you may have consultants and companies say, oh, well, you should optimize with respect to expected shortfall or this or that. The point of that condition here is all these examples are included. With standard deviation, you have to add the mean, but let's just forget that. So that's already the second important part. I'm working in really the nicest world of risk factors, risk models, ellipticals, and secondly, I look at a whole broad class of risk measures. Okay, now what are the results? The first result says, if you take any of these linear portfolios, so M is just a class of linear portfolios, we can calculate the risk measure. Here it is. The risk measure is the linear part, so it gets the mean here out, the linear part. Then we have sort of a covariance-driven second part. Oh, but as soon as I hear covariance, I know that I've got two good friends behind me that help me mathematically, as Cauchy and Schwartz, because that's like a norm there. But that's good to know. And now suddenly this rho epsilon1 comes. Somebody of, oh, it's written on the blackboard. Remember that, I think it was you who said, once Marius was defining spherical distributions, he said, oh, this very nice, these linear combinations. You can write them in distribution equal to a constant times one of them. Here is a one of them. So you see, this formula, again, is a fantastically explicit, nice formula. It gives us measure of risk on a multivariate setup, this linear combination, to the risk measure of just one very specific spherical distribution. Let's say the standard normal on this one. Sorry, not the standard normal, the normalized, the uniform distribution of the sphere. So very nice risk measure, a nice random variable. This is very important. This very much depends on this, and it only uses these properties of the risk measures. That's a very nice result. I mean, the proofs are there. I will not go into the proofs. It's much more important you understand the interpretation. Secondly, if this is positive, I had this before, alpha greater than a half, the inverse is, remember that? That's how I did the computation here. Remember? I wanted that positive, because I wanted this positive. That's the same thing as this here. That's the same condition here. If that is positive, my risk measure, not just value at risk, is subadditive. Why? The only thing is that I have to look at this here. The subadditivity, this is all linear. This can only play here. And sigma is A prime A, or AA prime. Now that looks like a square then. The norm. Square, the square root is the norm. The norm Cauchy-Schwarz, and you have the proof. Okay, you see, in this class, all these risk measures, including value at risk, are subadditive. So you see now why I start to call this was not just a joke, the fundamental theorem of risk management, because we're really discovering, let's say, somehow the broadest relevant class out there where these measures behave nicely. And I always said the second fundamental theorem of risk management is much more important. What are the properties if this does not hold? And then, of course, that's where a lot of the book is all about. But you first have to understand where life is nice and pretty as a risk manager. The third result, if I look at, I now assume the mean exists, I can look at my portfolio, then I can write the risk measure, and now I see I'm getting gradually to the concept of risk aggregation and later allocation. I can work it out, and I can combine the total risk minus the expectation, so it's the unexpected loss, you could call that. Okay, if you subtract the mean. And again, you can take here your quantile if it's a var. So this can be written as a combination of individual risks on each of the components. In some cases, you see the standard formula in Solvency II is in the background. Because if your risk measure is standard deviation related, you're just an epsilon away from the standard formula. And again, now I'm talking about principle-based risk management. I'm not writing down for you a strong belief that this must be the formula. No, I'm writing starting from really basic principles, I derive for you the basic solution of the problem. The standard formula, almost. But you see, I discovered that in that world. And if you want to write down this kind of formula for some risk measure in another model, fine. But if the measure doesn't satisfy one of these properties, I may have a problem in interpreting it. And you see, again, this is what the course gives you. The last result, do I give the... Yeah, okay, well, this is first moment finite. It's good. The answer, don't go to the next page. Suppose now the covariance exists. All right, now I have a second moment. I can go a bit further. And again, this is strictly positive. I get this linear portfolio, nothing happens. The rho L, well, this of course is the same thing. I just it's a translation invariant. So these two are, that one is that, so no problem. You can write it down. Then you can write down these coefficients in terms of the variance. You can say, well, what's the use of that? Now he's suddenly jumping away from the standard formula. I'm solving now another problem. And I think when we wrote that down, I think it's essentially Alex and Daniel who really came up with the first nice versions here. Now you're thinking of portfolio optimization. Now you think of 1950s, Markowitz. Now you think of risk-return optimization in a portfolio. Risk-return optimization in a portfolio, given a return, you want to optimize, minimize, or optimize your portfolio, the coefficients in your portfolio. Of course, all these constants are in the K rho, depends on rho, and of course on the lambdas, on your portfolio position. You want to optimize, given your risk measure, optimize the choice of your portfolio, the lambdas, so as to minimize the standard deviation. That gave Markowitz his Nobel Prize, of course, much more than that. He brought risk into the return discussion on portfolio. Now you see a very powerful result. Because what this theorem tells you, and I still remember those discussions early on, now we want to do value at risk optimization. We want to do expected shortfall optimization or risk measure ABC optimization on the same portfolio. What is this theorem saying? This theorem is saying if the risk measure chosen satisfies these very basic properties, then the optimal portfolio is the same. It's the same portfolio because you optimize with respect to the standard deviation. Of course, the values of your portfolio, the values you find out are different because they depend directly on the row. But you find the same portfolio. Now again, I come back to my tongue-in-cheek statement before. This, I think, is a kind of a fundamental theorem. This theorem tells you that the whole of classical portfolio theory in finance, insurance to a high degree, if you look at the asset side, works perfectly well in this world here, elliptical world. And of course, the second fundamental theorem is now, if we are not in that world, how do these things break down? So I hope I really was able to demystify for you some of those who are not day-to-day research mathematicians, the notation here. This theorem, I think, is highly relevant to calibrate your thinking in practice. And now you can go more in detail. Now you can take a specific row, you can work out. I will not do that. It's there, in the book is much more. I mean, this chapter, we really cut down dramatically because we had to make choices. But this theorem, I think, I want to tell you. The proof I won't tell you. What I just discussed with you, I gave you. These are disaster stories. You see Markovits coming here. Whatever, individual contributions, everything I've done for you. So it's all there. That is, now we go to, so this is a fundamental theorem, absolutely important on linear portfolio optimization, subadditivity, the whole properties, and why we taught you elliptical distributions. Risk aggregation, again, that's a huge area. So the EC, when you see that it's sort of, we use the word in the book economic capital. I'm not going into detail on definitions of economic capital. My colleagues can definitely do that much better. But let's say we have a capital, so the EC is just one abbreviation. We want to aggregate capital at underlying levels to capital at the global company level. And at the global, and if we call it economic capital, how can we sort of get global economic capital from contributions to subsidiary or sub-units economic capital? Well, you need a function, F, linear, non-linear, whoever, that maps the capital needs, the economic capital of the various entities to the global capital for the firm. This is the most general definition, I think, of risk aggregation. And I can look at it at many, many, many levels, also at product levels, as individual portfolio level. Of course, you can say, you can do simple summation. You can do correlation adjusted summation. Now you take your basic economic capital. I'm not saying how you may calculate them. We saw some examples before where you see some possible components of calculation, depends on your risk measure. And you may want to now bring in, not like here, you want to bring in some correlation if correlation exists. So the literature is full of this type of formulae. Now already you see this formula is surely close in the elliptical case to the formula I saw before. And you say this is not far away. If I can interpret these things here at the level of economic capital, which I can in certain interpretations, then I'm basically there. So in that sense, this is for me the fundamental theorem underlying risk aggregation the way many of you do it. Okay? And so what you discuss in the next pages, but I may go beyond that now, we'll see. In what follows, we show that correlation here, adjusted summation, is justified as a risk aggregation rule under various setups. And again, this is the whole thinking of risk, of principle-based risk management. Okay, it's not rules-based. You can just write down the rule and say, well, you know, it may be sensible in that or that world. No, this is principle-based, and we cover the principles under which this is a sensible rule, given the laws of the game we discuss. Okay, again, you saw this before. I don't think I will spend too much time on that, but again, you see this subtraction of the expectation. So it's the unexpected loss that you typically look at. Okay, that's now not. And of course, at the company level, this may be very relevant. I'm not talking at the trading level now, where this E is often 0. So I may have this mean in there. Let me just see, and of course, I still formulate the same problem. So the only main thing is that I now have a risk measure. Okay, just a translation invariant risk measure. I only use that for the moment because then I get here. I've tried to keep these rows as general as possible because I don't know which risk measure your regulator, your company is using. Let's see how general we can go, okay? And of course, now you can take the standard deviation risk measure. Of course, I have to add this expectation to get the translation invariance, finite variance. Of course, you can write a standard deviation rule. You can exactly write in that form. This is basically the formula I wrote down here. This is the same formula, okay? So in that case, a correlation adjusted summation follows by noting that this standard deviation has the right properties. This normalization you see immediately if you, the sum of the L's, you can write down as this 1-L, the covariance formula, and it's there. It's exactly what I've done here in 2 dimensions. Okay, so nothing special there. Again, if I say another principle where this kind of summation rule, aggregation rule is relevant or understandable, is now going to my fundamental theorem. Now I go to a much more general class. I assume the covariance exists, and I already formulated that to you, that the correlation adjusted summation is justified now for any positive homogeneous translation invariant and law invariant risk measure rho. That's exactly this theorem I mentioned to you before. Here. That's exactly that.
In the linear approximation of an elliptic distribution.
Yeah. Well, the linear approximation or the linear, you can say I may take the elliptical as an approximation already. So this is the elliptical, multivariate Gauss, multivariate T, multivariate hyperbolic, and then in that particular class. I'm not moving out of that. That's a totally different discussion, all right? But at least let's try to understand the principles. The book has much more, well, not much more. We try to go beyond in skew models, etc. Because the problem is, let's go back to this theorem. That's exactly the result now. Now you want to say, well, what happens to some of these properties if you move away from that condition? Then the first question I will immediately ask you is, what do you mean by moving away from that condition? Could be anything. It's like I always say to my students, well, I know what a linear function is. But now I want to have a result for a nonlinear function. Can be anything. The same here. If you say, no, it's not elliptical, but it's skew, that rather than, let's say, a multivariate T, I have got a skew T. Then we have many results on that. So now we really have to go down to individual models in your companies, or for the regulators, or in internal models. I can't help that. Or what's another way of moving from ellipticality? If I say I have tail behavior, still symmetric, but different in different directions. I got in one direction, I got Gaussian, there I got T4, T7. So you see, and then in some cases we can, but I hope you get a feeling that this kind of research is by no means easy. All right, it's by no means easy. So you cannot expect from us that's a very robust solution in some sense. So if you move away from the model in that sense, this is your benchmark result. You should benchmark your thinking on if you can understand that result. And more important, what's really behind these models, the nice world of ellipticality, which is still a big world, but it's a very restrictive in many ways. A very general class of risk measures is a wonderful result. I think I stress it because from the beginning that I think it was basically Alex and Daniel who came up with that result. I was really totally happy with that. And of course, since the book has been evolving, I think now we know what the best solution is, and we brought in things like the standard formula thinking, because it's so important under Solvency II. So I think we can nicely explain on principles where the standard formula is coming from and where it's useful.
Don't you see a danger? I mean, the standard formula is just assuming, it's just making these
Implicitly. Yeah, of course, yeah. I know. But this is true with any standard formula. A standard formula for me is a basic calibration point. Well, now we go into I should now talk with my regulatory colleagues. You realize that I didn't mention them explicitly in my speech too. Now I mention them many times. No, because now you have to sit together and say, for instance, my philosophy, but I should discuss it afterwards perhaps, is that I would keep standard formulas, internal models, the mapping to the capital, that's another issue, and look at discrepancies. If there are big discrepancies, then explain them. I mean, but that's a very different discussion. Well, you should know more about that.
No, going back to Coppolas, does ellipticality imply radial symmetry or not?
Yeah. It's
if you move up the board, oh no, it's not at the board anymore, but
yeah.
I can prove it one later.
Yeah. Yes.
Yeah. It's easy to see.
It might be almost there, I think. Okay. Anyhow, so that's a very strong assumption. But I'm not saying the standard formula is wrong or right. I'm just saying in that world, which for us is perhaps the most general world, it's the right one based on principles. I'm making a strong statement here. Okay, let me move to, I think this is, I will miss this for the moment. I want to go to this problem. So I hope you saw I gave this little summary with the two stories of expected shortfall value at risk being close together in the Gaussian world. Univariate Gaussian. Very different in the T world. That's just heavy-tailedness, all univariate. I gave you the example of subadditivity for the bivariate Gaussian. It's always a nice exercise because you explicitly see in the calculation what you need. That's the most important line here. All right? And then I said to you, okay, once we have that, we now can generalize it to what I call this fundamental theorem of quantitative risk management, which is the big theorem I mentioned to you. I think that's, for me, the really important result. From there, we can derive many results which are related to some of the formulas you use. And what we do is we tell you exactly for which risk measures and exactly under what conditions. Plus, and I think this, I hope, is for most of you an aha experience, this statement here. The 4, I could have challenged you whether you knew the 4, that portfolio optimization under any class of such general risk measures is equivalent to Markowitz optimization. You find the same portfolio. You find, of course, different values because you measure your risk differently, but you find the same portfolio, which I think is a nice result. So that I would hope is really new to you. This we wrote more because it really gets you into the language of the standard formula. If you can go away from this discussion with this I understand, then I think we have achieved a lot. Now what I'm going to do is I'm going to introduce a technique. Now I'm going really to my current research. And I will ask perhaps after the break, if I can, for Marius to do a rearrangement.
Well, half an hour we can have in the afternoon.
We can get half an hour. All right, wonderful.
Otherwise we will run into problems with credit. That's the best.
Is that okay?
Half an hour should be.
Half an hour. So you have half an hour. Well, yeah, you get it. I think you had an appointment going swimming, perhaps. Or so.
You also talk about capital allocation.
Oh, yeah. Oh, it's sure true. Yeah. No, wait. As Frank asks is. Yeah, I know it comes after. No, wait. Capital allocation. No, this I can do. No, I can do it. And the Frechet problem with the this is doable in the extra half an hour. No, I'll get there. Capital allocation. Because here I want to introduce to you another famous result. This is Euler, Leonhard Euler, by far the most important Swiss mathematician, perhaps the most important mathematician ever. And of course, my Russian friends would say, well, he's basically Russian because he spent most of his life in St. Petersburg. But anyhow, it's incredible what this person has done. Risk allocation. Well, the allocation problem, of course, now we go to RORAC. We want to have risk-adjusted return on risk-adjusted capital. So now I want to look at expected profit of investments over risk capital of the investment. I'm happy, and I'm always taking you, but I'm happy that you take risk, but that you want to have a high return, but of course you have your risk. So how do we compensate for that? All right? So again, the risk capital of investment J with loss Lj can be computed as follows. So we have the risk capital of totally is the risk capital underlying the total position. And now we want to allocate this money, rho L, the total capital, and this of course somehow I already discussed it. You put available, let's say, 100 million risk capital, typically value at risk-based for most of the banks, 95%. They typically do 95% one-day allocation. And U5 are my different desks, the Asia desk, the European desk, the US desk, whatever. And I want to calculate this 100 million among you. The risk allocation rule is just this allocated capital to the J different positions. How do I do that? So you want to have, at least to start with, an additive formula of distributing that money in a principle-based way among the various players, among the various people in your investment department. The same is true, of course, in the actuarial side. Here's a formal setup, and I think I will quickly, there's not much more on the slides, I think but we never mind about those things. I've got, again, a linear portfolio. Later, I will typically take the lambdas equal to 1, but it's not important. I take a linear portfolio. I take a risk measure. In allocation, well, portfolio is there, breaking up in subunits to different desks. Allocation is there, so I must have a risk measure. So I must somehow measure the total risk of my portfolio and then distribute the risk in an additive way among the various players. So I introduce, and of course it depends very much on the weights I put in the various portfolios. So here I've got a function lambda, which is the risk measure of my linear portfolio with weights lambda. Okay? Now, a very important observation, if my risk measure, which most standard risk measures are, evaluate risk expected shortfall, is positively homogeneous. So LTX is TLX, positive homogeneous of order 1. If you have positive homogeneous of order k, is LTX is t to the power k Lx. Quadratic function is homogeneous of order 2. Linear function homogeneous of order 1. No constant, of course. So if it's positively homogeneous, then for free I get an allocation. This again, principle-based. If your principle is the theory of risk measures which are positively homogeneous, if you're happy with that, then I'm giving you an allocation. Not I'm giving you, Euler gave you. This is a very nice result. If I would have 5 or 10 minutes longer, I would like to prove this result on the blackboard because it's very easy to prove. Euler proved something more general. But Euler proved if, so this is a function from RD, you can take positive weights, now it depends long and short position, but let's say long in this particular setup, is a function RD plus to R, because it's a number, which is homogeneous of first order. If I assume it's differentiable, I can take derivatives, which is a condition, depending on the risk measure. Then Euler said that the only way you can get that is, well, the way to get that is you take the linear combination of your weights, your portfolio weights, and the derivative of this function with respect to lambda. This is, take the example yourself, and you can do it in 1 second, as a function x1 plus x2 is homogeneous of order 1. And write down the right-hand side, and you see it's trivial. x1 plus x2, you take the derivative with respect to 1, then you get 1, and you multiply by x1. You take plus the derivative with respect to this x2, that's 1, and you multiply by x2. So it's trivial. It's not more complicated Euler than that at this level. So this is not a deep result in one direction. Euler did more. So this is the Euler principle, and I still remember, sorry, I hope I'm not bothering you when I say I still remember, but I do still remember, when this Euler principle first came on the carpet, again, I think in Risk Club, and the two names to mention now are Dirk Tasche, who is now a regulator at the FINMA, came over from the Bank of England, was a postdoc at Risk Club also, Dirk Tasche and Stefan Bernecker. Who knows Stefan Bernecker? Yeah, colleague of you, Swiss Re. Yeah. And this again shows the close collaboration in Risk Lab and the insurance industry, because I think Stefan Bernecker might maybe first putting on the table, say, it's like Euler. And so they wrote a very nice paper on risk allocation. And so here it is. So now it's risk allocation is, you come to me, Frank, with your risk measure. If it's homogeneous of order 1, this is your allocation rule. And now you can look in the book as I think 3 examples, 3 or 4 examples, I think. Value at risk, expected shortfall, and expectiles. Just in anticipation whether or not people like them. Isn't it? Close to that.
Variance, value at risk, and expected shortfall.
We don't do expectiles?
I don't think we do expectiles.
I forgot. Never mind. But yeah. Anyhow, so you now take your risk measure. And here's one example. So the Euler capital allocation principle, now your capital are these weights. You take for lambda equals 1, because you look at the sum of your, okay, you take this formula here for lambda equals 1. If you take the sum of the L's, you have your individual subunits. So that's the Euler principle. And now you take your risk measure. And now you get the covariance principle. If your risk measure, if your standard deviation here, which is homogeneous of order 1. I've not used anything else. Homogeneous of order 1. Only that, I assume. Then you can calculate. The only thing is you have to calculate of this, with respect to lambda, this quadratic form. But taking the square root the derivative of a square root gets you 1 over 2 of this, the standard deviation here. And the 2 also drops out because you have to take the derivative of a square in the lambdas. Of course, I do it multivariate here. But you should see immediately, oh, yeah. From this, it's just one line to get to that here. And this is your covariance principle. So the covariance principle, which is perhaps the most widely used principle in insurance, definitely to some extent in finance, is the Euler principle of risk allocation. Now you can say, I want to take value at risk, I want to take expected shortfall. In the book, you find the formula. It tells you if you're risk managing with value at risk or expected shortfall, then these are the marginal contributions to your risk factor, to your allocation, and you can nicely interpret them. And then again, you can do a bit more, but I'll leave it there. Let me take, as the first time I do that, take you 5 minutes to introduce Marius for this afternoon. Is that okay? I know it's short, Frank. It tells you at least there's a principle there to get these things. Let me finish with this in 5 minutes, and Marius will take up later, and I think he can finish that in half an hour with the rearrangement algorithm. Now I'm moving to the world of model uncertainty. And so it really ties up a lot of problems we've seen now before. This class was introduced before, the Frechet class. Again, I stay with the same problem, a linear portfolio, a linear combination of risks. And I'm interested in I leave out the weights. The weights are not important. I can put them in the LJs. The point is, the key word now is model uncertainty. Because I now assume I'm interested in a linear portfolio, as always we do, approximatively, or as a construction already to start with. And now I only assume that you know the marginal distributions. That's the only condition you have. Let's say I have the sum of 10 normal random variables, all standard normal, but I don't give you anything more. I'm not saying they're multivariate normal. No, not at all. I'm just saying each one of them is normal. No condition, not copula, not joint distribution, not independence, nothing. Just give you the margins. So that means you're agnostic when it comes to interdependence. So you want to find now, for a given risk measure, and again, of course, we have to specify risk measures. This work we have done so far, and this is now summarizing a lot of recent work we have done, especially in my group in Zurich, for value at risk already for many years, expected shortfall, and expectations. Here I know we have done it also for expectations to a high degree. And of course now there's a whole group in Waterloo, in Brussels, Milano, many people now working in Freiburg, Rüschendorf, many people. Now I want to calculate these numbers. So what are these? The best and the worst risk measure you can achieve if you only assume marginal information. So what's the worst, if rho is the var, what's the worst value at risk? The highest capital, let's call it capital, you have to put aside across all portfolios with these marginal distributions given. That means it's an optimization problem over copulas, because that's the only link for the joint. You need a joint model. You cannot calculate the risk measure, a non-trivial risk measure, if I don't have a joint model. You don't get it from me. I don't give you a joint model. You only have the marginals. So this is an optimization problem now over all copulas, really. And you can also do the lowest. And in particular, let's say if rho is expected shortfall, this, let me now, well, this is the only easy one. Though is the worst expected shortfall of L, given I specify only the margins. Now expected shortfall is subadditive. That's one thing, it's important. And secondly, the worst is achieved under comonotonicity. And that gives you, this is the solution. All these other numbers are difficult. There's no easy solution. And the summary, and here I stop, I think, and that leads nicely to you. The summary is that, I hope you all understand this question. The question is very easy. What is the current state of the research? And there's perhaps 50 papers in the background. For two-dimensional, let's say, if you come to me and say, my first risk is standard normal, my second risk is gamma, and you say, what's the worst value at risk of the sum of these two across all possible portfolios? Well, let's say gamma exponential for the moment. The worst value at risk, if I add up them for the sum, if you don't know anything, I can give you an analytic formula. That goes back to Makarov, a student of Kolmogorov, and Rüschendorf independently in the early 80s. That's a case we can solve explicitly. But of course, we're interested in high dimensions, and not stress 3 and 4, thousands or so. And that's where the numerics come. For greater than 3, if I ask the same question, if you come to me and you give me a number of log normals, a number of gammas, a number of exponentials, I've got 10 of them, I add them up, I know the distributions exactly. No statistics for the moment, we can bring in the statistics if you like. I know them exactly, you add them up, and you want to have what is the dependence, the interdependence between these 10 risks, marginal risks. What's the worst value at risk at a level of 99.5%? I cannot give it to you. I can give it to you numerically, but not analytically. If, however, you come to me with the same question, but you're all gamma 3-1, i.e. if you're a homogeneous case, I can give you the formula. But that's highly non-trivial mathematical work. Some of it is briefly reviewed in the book, but that's really getting now into current research. So summary here, answering the question, the model, the dependence or the interdependence model risk of linear portfolios given full marginal information, or statistical, but let's say full marginal information, but nothing about dependence, that problem is highly solved in this case here, non-trivial, mathematically highly non-trivial, but it's solved now in various papers we wrote and colleagues wrote. In the homogeneous case, hardly any analytical results are available. Hardly any analytical results are available if you give me some extra dependence information. If you say, no, I have some extra information, I may have finite second moment and I have some, let's say, all the correlations lie in a certain area. If you tell me all the correlations are positive, I can solve it, but that's one of the few cases. So you see, I can go from the fully agnostic situation, I don't know anything of the dependence, to a full specified model, let's say elliptical or something like that. Reality lies in between. I only have partial information. What can you calculate? So in the inhomogeneous case, which every case I know is inhomogeneous, we have to use numerical methods. And this is a very, very powerful technique. It's a so-called rearrangement algorithm. I think it's really, I think it's one of the very important contributions recently to the field. It goes back to Rüschendorf in Freiburg. Then Puccetti Rüschendorf wrote a paper, and then we wrote a paper bringing it to risk management at the level of value at risk, and then there was an explosion of results, and now so many interesting work. And I think after the break, for half an hour maximum, Marius will give you a brief overview of the kind of questions on a concrete example you can solve. It's time for lunch. Okay.
So, as Paul already said before the lunch, we will now focus on the inhomogeneous case, so all our marginal distributions given and not necessarily the same. Of course, you can also apply it if they are the same. And we studied numerical methods, one method especially the rearrangement algorithm to compute worst and best value at risk, also best expected shortfall for the sum of our risks. So the setup is we have given very specific marginal distribution functions, and on top of that we have no other information about the underlying copula. Yeah? So in some sense we want to optimize over all multivariate distribution functions with these given margins, so over all possible copulas and these given margins. And we are interested in the so-called dependence uncertainty gap, which is essentially the worst value at risk and the best value at risk, the largest and the smallest among all these possible copula models. Yeah, so that's it, and for the expected shortfall, essentially the same. I will mostly focus on value at risk here. Right? Worst expected shortfall is trivial, as Paul said, it's simply the sum by sub-additivity and comonotonic additivity, and the best value at risk you can treat similar, best expected shortfall you can treat similarly as value at risk. Good, now the rearrangement algorithm. The good part is you only need to understand two things to understand the algorithm. Namely, you have two vectors, just two vectors of numbers, same dimension, what it means to be oppositely ordered. So two random vectors are oppositely ordered if the smallest value of the first one lies next to the largest value of the second one, the second smallest of the first one next to the second largest of the second one, and so on. So they're ordered oppositely, as the name says, very intuitive. And then you need the minimum row sum operator. So you imagine you have a matrix, D columns, and each column represents a discretization of the corresponding marginal distribution. So you always have a capital N by D matrix, capital N being the number of discretization points, capital D being the number of losses. And the minimum row sum operator then just computes the row sums, yeah, so essentially the sum of your losses, and picks out the minimum of these N, capital N, many elements. And with these two quantities, you can then, yes?
Just to understand the indices here, so you will later use it to a situation where you have a fixed number D of risk factors, and this capital N is sort of discretization, so that is typically going to be large.
Yes, we're gonna, yes. Yeah. So N, you can choose, the larger N, the better the approximation. D is typically fixed, but I also can look at it as a function in D even, yeah, just to study the performance of my value at risk and expected shortfall bounds. We will come to that. So the rearrangement algorithm then, and this is the presentation for the worst value at risk, works as follows. So I have a typically given confidence level I'm interested in, and I have for my D marginal distribution functions the corresponding quantile functions, and I have capital N, the number of discretization points of these marginal quantile functions, and an epsilon tolerance that tells me when to stop the algorithm. So now I want to approximate worst value at risk, the largest value at risk. Now, since I discretize my marginal distribution functions from above and from below, I get corresponding bounds on this worst value at risk. So I actually compute bounds on the worst value at risk, yeah? And I can do the same for the best value at risk then in the end. So I essentially get two bounds, hopefully quite sharp, and then you can take the midpoint, for example, as your estimate for the worst value at risk. Good, and so to compute the lower bound on worst value at risk, you have to define this N by D matrix, which contains in each column the corresponding discretization of the marginal quantile function. So that's the discretization from below, and then for the upper bound, you do the discretization from above. Doesn't matter much. You have an n by d matrix of numbers essentially to treat. There's also, you can randomly permute each column just to avoid non-convergence, but that's not an issue now. So now you have this n by d matrix of numbers. Forget about anything else. You just have an n by d matrix of numbers, and you do a certain kind of operation on that. You start iterating over the columns, one at a time. And every time you sit on a specific column, you consider this column and you reorder it oppositely to the sum of all other columns. Because oppositely reordering, and you had this argument for the lower Fréchet-Höfting bound, only makes sense with respect to two vectors at a time. So I consider that very column I sit on, and I consider the sum over all other columns. That's, of course, then also just one vector with n numbers. So I iterate over all columns, and in the jth column, I take this column, I compute the sum over all other columns, and I oppositely reorder the jth column with respect to that sum of all other columns. Why? That's a different story, but that's how the rearrangement algorithm works. And so I do that essentially until I satisfy it, so after rearrangement over all of the columns, I then look at this newly rearranged matrix, and I compute the new minimal row sum. And I do that whole procedure. I go through the whole matrix every time I compute the minimal row sum and so on, until that minimal row sum doesn't change too much anymore. That's the ideal. You can also do it until all columns are oppositely reordered with respect to the sum of all others. That would be even stricter. And then that minimal row sum I compute in the last step, that's going to be my lower bound on worst value at risk. And you can do the same, but you just feed it with a different matrix of quantiles, upper approximation from above to your marginal quantile functions to get an upper bound on worst value at risk. These two bounds are typically quite small, but that of course depends on the number of discretization points. And then you take this interval as the so-called rearrangement range, or the midpoint, for example, as your estimate of worst value at risk. Now this is the algorithm. That's how the algorithm works. There's a little bit of intuition, and the theory behind here is, as Paul stressed this morning, extremely complicated. But I just want to, in one picture, try and give you the intuition. So I have the sum of my losses, and if I manage to minimize the variance of my losses in the tail, then this mass 1 over alpha is more and more concentrated here further out, and that pulls value at risk to the right. The more and more I pull my mass I've left here together, the more and more this pulls out my value at risk, the larger and larger my value at risk, and that pushes me towards the worst value at risk. That's the ideal. So ideally, I manage to get joint mixability. That means with probability 1, almost surely, my losses, the sum of my losses is constant. Then I put all of the mass essentially in one point, and that gives me the largest value at risk. But that's not always possible, and this is only an intuitive argument. But I hope it's very tricky to explain this. I mean, this is, Rodu Wang once told me this is how he would explain it, but the theory is actually not exactly precise. But that's the ideal. You want to push more and more, concentrate that mass, therefore minimize the variance. Minimize the variance, therefore push the mass further out and pull value at risk further out. That's the ideal. And of course, by looking at the minimal row sums and increasing the minimal row sums, more and more you concentrate the mass that you will see in examples as well. So that's the intuition. Let's look at an example. So here I have just 4 discretization points. I have 3 losses essentially. And I sit on the first column, and then I compute the row sum over all other columns. And you see that's increasing, so I have to rearrange my first column in decreasing order. And then I continue with the second column. I build the row sum over all others. I get 5, 5, 6, 9. And then I rearrange that second column with respect to the sum over all other columns. Now, there's already an interesting point here. You see a tie here. So it's not so clear. Those are the 2 smallest numbers in here. So the 2 largest in the second column, 5 and 7, have to be located next to 5 and 5, so in the first two values. If you don't use a stable sort algorithm, you might get different results. But if you use a stable sort algorithm, it leaves the original order in this case, so you get 5 and 7. But it's not really clear what 7 and 5 would be equally possible. Yeah? So there are some numerical issues. There are a lot of very interesting questions around. I cannot go into detail here. I force myself not to. But this is how the algorithm works. And then you continue with the third column and so on. And essentially, you can iterate until you end up here. And you can check that each of these columns is oppositely ordered with respect to the sum over all others. And that's where you stop. You then look at the final minimal row sum. So what are the row sums? 10, 10, 11, 10. The minimum is 10. So that's my estimate for worst value at risk. Now, another example, and this goes back to a paper that Paul mentioned earlier. So if you have just this very simple example, 1, 2, 3, 1, 2, 3, 1, 2, 3. There you do the rearrangement. After one step already, you see that all columns are oppositely ordered with respect to the sum over all others. Now, we are essentially already done, so I compute the row sums, and I take the minimum as my worst value at risk estimate. Now, this is not the optimal rearrangement. 1, 2, 3, 1, 2, 3, 1, 2, 3. I can, of course, say 1, 2, 3, 2, 3, 1, 3, 2, 1. Yeah? And then I get the row sum 6, 6, 6. So my minimal row sum is 6, which is even larger. And it's not clear, it's not the optimal value, but that's what the rearrangement algorithm gives us. So that's an example where the rearrangement algorithm does not give the optimal. So here are some examples I reproduced from, I think it's table 8.1, 8.2 in the book. So you look at Pareto margins, essentially high quantile, worst value at risk, best value at risk under comonotonicity, so upper Fresher-Höfting bound, value at risk under independence of the losses. Yeah, there you see for heavy-tailed Pareto distributions, really heavy-tailed Pareto distributions, you see that the value at risk under comonotonicity is even smaller than the one under independence. Yeah, so that's a super additivity example, if you like. Yeah, and there are other interesting observations here. For example, how does value at risk worst value at risk compared to worst expected shortfall as a function in D. So for the larger the dimension, the more worst value at risk can be approximated by worst expected shortfall. So for large D, you have this result. It's a whole proposition explained in the book. Can also kind of quantify the
theta is the Pareto parameter in the second case, because the theta 2 is an example of the second line.
Oh, yeah, that should be theta, correct. That should be theta, yeah, that's correct, yeah. And also something, an open question for you essentially, if you plot this as a function in D, then you will see that the worst value at risk is in log-log scale linear. Yeah? So numerically, it looks extremely linear, but as a function in D, I don't think theoretically it's known even for Pareto margins why that holds. Yeah? So there's a lot of new material here. Good.
One little comment on that. That's just for the example comment.
Yeah.
The fact that we have D equals 8 and D equals 56 is because we started working on these problems because of operational risk. The Basel Committee, Basel II operational risk, you had the 8 business lines and 7 risk types. Banks were typically organizing analysis of the loss distribution approach. It's changing now. Aggregate data up to 8 business lines, analyze the business lines separately, so you've got these 8 models of business lines and VARs. You add them up, and then you use a diversification argument. And that's exactly why we started working on these problems. Because we say, well, you can use any argument you like, but we will give you the real bounds that you can get. That's why we're looking at it. The 56 would be then if you have models for each cell. So that's the example. So I think it's good to see where the questions came from. That's the reason we wrote our paper on Circle Banking Finance.
Good, so let me now just give you a little bit of a walkthrough through an R script that replicates some of the results. So we have the QRM tools package for the algorithms, and I use some data from QRM data. I use Google stock, Apple, and Microsoft in a certain time period, and I add essentially 2 more marginals that I just specify through the corresponding quantile function. So I use as first 3 marginals empirical distribution functions of these risk factor changes. So those are just your empirical quantile function. You see in here the quantile function in R. And then I essentially add to that the Pareto quantile and the log normal quantile function. So the algorithm is specified in terms of the quantile functions. So I have essentially D equal 5 here. And then there's a very basic version of the rearrangement algorithm implemented here. So, and I hope you kind of can at least extract exactly what we discussed on the slides. So essentially, you loop over your input matrix, and when you sit at the jth column, then you sort the jth column in opposite order, so decreasing order, versus the ranks of the row sums over all other columns. Yeah? Even handling a little bit of ties here. Yeah? So you see, essentially, you can do it in one line in R. Yeah? So this is where the magic happens. Then you compute the new row sums, the new minimum row sums. You check how that differs from the previous minimum row sums after the previous iteration over all columns. And if that satisfies the tolerance, then you stop and you return that new minimum row sum as the worst value at risk. So this is a very basic example how to implement the rearrangement algorithm. You can apply it. Let's say here the confidence level is 99%, n is about 1,000 here as number of discretization points. I discretized the tail of the marginal distribution functions beyond the alpha quantile. So this is very easy to do here as well. And then I apply to these discretization points on alpha 1, essentially, my marginal quantile functions. The first 3 components are the empirical distribution functions. The remaining 2 are Pareto and log normal. And then I can compute the worst value at risk. And so I can also, so that's essentially it. I check versus stopping a little bit earlier, and that gives me roughly the same result, so that's fine too. I can use the internal function we have in the package RA for the rearrangement algorithm, which is quite a bit faster in higher dimensions. So I can also look at that, and it returns a lot of things here. It returns the rearrangement gap. It returns lower and upper bound, essentially. It returns the corresponding absolute tolerances reached for the lower and the upper bound of worst value at risk. It returns whether it converged in the sense that it reached these precisions, the number of rearrangements used, the corresponding minimal row sums as we go along. So you see how they change and how they grow, you can plot that and so on. There's a lot more. There's the input matrix essentially, and there's the rearranged matrix, so that also has a meaning and use, so you can use that as well. There are a lot of examples on the help file as well. Just do !RA and you get there. There's also an adaptive version which does not require you to specify your own number of discretization points and has some other advantages. We are currently working on that, so that's there as well. Then here is an example I reproduce essentially from the book. So applied to worst value at risk, best value at risk, and best expected shortfall. So best expected shortfall is available since last Friday essentially. And then here, I would like to show one last feature. Here are the 2 toy examples you saw on the slides, so the 4x3 and the 3x3 example. And we have a trace feature as well, and I think this is very nice. So with the trace feature, you can actually see what the algorithm does. So let me just go down here. And then you see the original matrix that was built, and then you see the current column that's rearranged. You see the sum over all others, and you see the overall row sums on the right side. And then you can go through one at a time, and you see how the minimal row sum increases and so on up to the very end where all columns are oppositely reordered to all others, and the worst value at risk estimate is then found as 10. So there are a lot of things computed underneath, and there's a lot of work coming as well. There are a lot of numerical questions, unsolved questions with the ties as well, and so on. But that's very roughly, in a nutshell, how the algorithm works. Thank you very much.